Stangibelisco here to explain a phenomenon that I've always found rather fascinating. I call it, for lack of a better term, the bulb paradox. It starts out with two light bulbs of different wattage ratings. Well, different wattage ratings meaning different filament resistances. Let's just suppose that we have a light bulb with a 2 ohm filament resistance here and a light bulb with a 4 ohm filament resistance here, and they're both connected to 12 volt batteries. Now, how much power is each one of these bulbs going to consume? Well, remember the formula P, power in watts, equals E, the voltage in volts squared, divided by the resistance in ohms. So in this case, E squared over R is 144, that's 12 squared, divided by the resistance, 2. Wow, that's a pretty heavy light bulb there. We're talking 72 watts. That's a pretty bright light bulb, eh? For a 12 volt battery, you better have an automotive or a marine battery to deal with that. 4 ohms, E squared over R, 144, divided by 4 equals 36 watts. Just half the wattage. So you have a filament with twice the resistance, and it consumes half the wattage. Well, that makes sense, right? So you have what you might call, well, we can do away with the 12 volt battery for the time being, because we're only going to need one in the next scenario anyway. This is at 12 volts, this is a 72 watt light bulb. And this is a 36 watt light bulb. You've seen light bulbs rated with different wattages, usually intended for 117 volts RMS AC. Give or take a little. Sometimes it can be as low as 110, sometimes as high as 130 or so. But nominally 117 volts. You might see, a 15 watt incandescent light bulb or a 40 watt fluorescent light bulb. Or now they've got these newfangled LED and compact fluorescent bulbs. A 2 watt light emitting diode bulb might consume 2 watts of actual power, but radiate the equivalent of what would be maybe a 25 watt or a 15 watt incandescent bulb. But be that all as it may, it's a little bit of a side issue. What I want to find out is what happens to this 72 watt light bulb and this 36 watt light bulb if, rather than running them independently off a 12 volt battery or connecting them in parallel across a 12 volt battery, in which case they'd still each consume the same wattages and the total power would be consumed would be the sum of this of these wattages. Suppose that instead we connect these light bulbs in series across a single 12 volt battery. Which of these two bulbs, the so-called 72 watt or the so-called 36-watt bulb is going to burn more brightly. They're going to have, let's just assume, for the sake of argument, that their filaments have the same resistances. Actually, they won't, because they'll burn at different brightnesses, and therefore they'll be hotter, or, well, actually, they'll both burn cooler than usual, and that will cause their resistances in effect to decrease. But let's just suppose that they're very special incandescent light bulbs, ideal incandescent light bulbs, and most are pretty close. 2 ohms and 4 ohms of resistance. What we have now here is a total resistance of the sum of 2 and 4 ohms, or 6 ohms of resistance. That resistance, 2 ohms plus 4 ohms. 12 volts. Remember Ohm's law? Current equals voltage divided by resistance, where we have the current in amperes, the voltage in volts, and the resistance in ohms. So in this case, 12 volts, and the net current is, or the net resistance here is 6 ohms. So 2 amperes is the current flowing at any point in this circuit. No matter where you put an ammeter in this circuit, you're always going to have it read 2 amperes. So how much power will each of these bulbs actually consume now that we have them in series? Well, remember the formula. Power in watts equals the current in amperes squared times the resistance in ohms. The current here is 2 amps, so I squared is 4 in both cases. So we have 4 amperes, or amperes squared, times 2 ohms equals 8 watts actual resistance. A lot less than 72 watts, wouldn't you say? And over here, the current squared times the resistance, 4 times 4 equals 16 watts. So what we have here now, instead of a 36-watt light bulb, is a 16-watt light bulb. And what we have here, instead of a 72-watt light bulb, is an 8-watt light bulb. Rather than twice as bright, or in effect twice as bright, or much brighter certainly, when they're connected individually, the lower wattage 36-watt light bulb, rated for 12 volts, actually consumes twice as much power as the higher wattage rating light bulb does. In other words, the dimmer becomes brighter and the brighter becomes dimmer when you connect them in series rather than in parallel. You might want to try that sometime, making sure that you stay safe if you use 117 volts AC, but get to incandescent light bulbs. They have to be incandescent, the old-fashioned kind, and they're getting kind of hard to find nowadays. But you can still find them if you've been hoarding them, or if you want to go to an antique shop. Get them. Get a 15-watt bulb and get a 25-watt bulb, quote 15 watt and quote 25, and connect them in parallel, and you'll find that the 25-watt bulb indeed does burn more brightly. But if you connect them in series, you'll find that the 15-watt bulb, quote unquote, actually burns more brightly than the quote unquote 25-watt bulb does. The universe saith, the greater shall become the lesser, and the lesser shall... Now I grow profound, unnecessarily and ridiculously profound. Shut up, Stanley. Shut up! But you get the point, right? Stan Gibilisco signing off. Until next time, so long.